Okay, today we're going to talk about continuity of fluid flow, volumetric flow rate, and work. So the continuity of fluid flow is pretty interesting. And then for fluid power, for hydraulics especially, it's very easy to understand. It basically just says that the rate of which mass enters a system is equal to the rate of which mass leaves a system. So it just basically says that inside the system, mass is not magically being disappeared, or it's not being created. So which is good. That's good for us. But since our fluids and hydraulics are incompressible, that also means the volume that that fluid enters is also equal to the volume that exits. So in this case, if we have volume entering here and exiting here and here, then that means that the volume entering at 1 and 2 has got to be equal to the volume exiting at 3 and 4. Volume entering added together at 1 and 2 is equal to the volume added together at 3 and 4. So what are some implications of it? What does this actually affect? Since volume is equal to the area that some of something times the distance, then we can say that when you have two different pistons with two different areas, so we have piston 1 with some area and piston 2 with some different area, then because the fluid that's moving from piston 1 to piston 2 is equal, then the distance, the displacement of piston 1 is going to be different than the displacement of piston 2. So if the area is half, okay, then if the piston 1 moves 2 inches, then piston 2 is going to move 1 inch. Okay? Now this is area, not diameter, because area and diameter are different, right? So this is sort of related to our idea of work as well. Work is force times displacement. Okay? So if, for example, we have some cylinder that moves some distance, if the second cylinder moves a shorter distance, then if the work is the same, then the second cylinder is going to have a larger force. So there's an implication of that as well. So this sort of relates back to our hydraulic multiplication of force. So again, we're looking at cylinder B here powering cylinder A potentially here. If cylinder B moves 20 centimeters, then cylinder A is going to move 2 centimeters. If our force is 10 newtons, then on cylinder B, then the force on cylinder A is going to be 100 newtons. So basically, cylinder B is going to move 10 times further than cylinder A, but require 10 times less force. If we figure out the amount of work, the work remains the same. So let's just look at this for a second. So we have 100. Let me fix this real quick. So if we look at the work, we have 100 newtons times 2 centimeters. We have 200 newton centimeters. And if we look at the other side, we have 10 newtons times 20 centimeters. Again, 200 newton centimeters. So the work is the same on both sides. That's an important concept. Work in has to be equal to work out. Now there is efficiency that we have to talk about later on, but for right now we're assuming 100% efficiency, so work in and work out will be the same. Alright, let's talk about volumetric flow rate. So volumetric flow is just a volume divided by time, right? But it can also be area times velocity. And that's pretty interesting because if you know the area of some diameter and you know the volume of fluid that's flowing through it, then you can find the velocity of that fluid. So a lot of times we are going to use meters cubed per second or liters per second, and we can also use feet cubed per second or gallons per minute. GPM is a very common one. So what are the implications of the continuity equation and fluid velocity? Well, we know that if a fluid, for example, entering this pipe here is got to be equal, the volume of fluid is got to be equal to the volume of fluid exiting the pipe. That also means the volume of fluid per rate of time is going to be equal to the volume of fluid per rate of time exiting. So the volumetric flow rate is going to be equal on both sides of this pipe. The fluid has nowhere to go, and it's not being generated inside the pipe. So it's got to be, the two GPMs have got to be the same, or the two volume per unit of time is got to be the same. But the area of the entrance of the pipe is greater than the area of the exit of the pipe. So the volumetric flow rate is velocity times area. So if our area is greater on one side than it is on the other, then our velocity on one side is going to be less than. So if our area is greater here, so if area is greater, then velocity is going to be less. Whereas on our area is less, so our velocity is greater. Alright, so here's an example. We have a cylinder, and it's got a 10-pound force applied to it with a diameter of 0.5 inches. The cylinder experiences a displacement of 0.5 inches. This causes a second cylinder to extend that has a diameter of 2 inches. So let's just draw this out real quick. We have cylinder 1. And it is connected hydraulically to cylinder 2. Right, cylinder 1 has a diameter of, let's write this out, diameter of 0.5 inches. It has a displacement of 5 inches, and it has a force of 10 pounds. Cylinder 2 has a diameter of 2 inches, but we don't know its displacement, we don't know its force. Alright, so find the pressure of the fluid, the volume of fluid being that's displaced, the work done on the cylinder, the force applied by cylinder 2 to a load, and the displacement of cylinder 2. So first thing we probably should do is find the areas. So I'm going to go ahead and do this right here. Area of 1, area of 2. Area of 1 is 0.25 inches squared times pi. And area of 2 is going to be equal to 1 inches squared times sorry about that, times pi. Area 1 is going to be 0.196 inches squared. Area 2 is going to be equal to 3.141 inches squared. So our pressure at 1 is equal to force divided by area, so 10 pounds force divided by 0.196 inches squared equals 51 pounds per inches squared. So we know that P1 equals P2. This is Pascal's law, right? Remember that. P1 equals P2. Sort of cramming everything in because I know I'm going to need some space. So P2. So if we want to look at force 2, we can just take P1, which is also equal to P2, and that is 51 pounds per inches squared. We can times that by our area, which is 3.141 inches squared, and that's going to give us a force of 160 pounds. So there we've got the force applied to some load of cylinder 2. We have the pressure of the fluid. Let's find the volume of fluid displaced. So volume at 1 is equal to area times displacement. It's a simple equation that we should know. So V1 equals, that's area 1 times displacement 1. So area 1 is 0.196 inches squared times the displacement, which is 5 inches. That's going to give us a total displacement of 0.98 inches cubed. So we know that V1 equals V2 because of our continuity equation. So V2, or I'm sorry, we should probably look for, instead of V2, S2. It's just going to be our 0.98 inches cubed divided by our area, which is 3.141 inches squared. And we should get a displacement of 0.3. That is not looking pretty. 0.312 inches. So we got displacement and we got the volume of fluid displaced. So let's look at the work. There's a couple ways we can get this, but we're going to try to see if we can get most of them. So one way we can get it is going to be our force times displacement. So 10. Sorry. This is going to be work on 1. So we'll do work 1 equals force times displacement, so 10 pounds force times a displacement of 5 inches. It's going to give us a work of 50 inch-pounds. There you go. If we look at work 2, or the work out, it's 160 point, it's actually 160.22, but I'm just going to go ahead and 160 pounds force times a displacement of 0.312 inches equals, again, 50 inch-pounds. There's another way we can do it, and that's with pressure. So I'm going to go over here. It's going to be 51 pounds per inches squared. And times this by 0.98 inches cubed, which is our volume that was displaced. And we end up with 50 inch-pounds again. And the pressure and volume on both sides is actually equal because of this right here. So pressure at 1 is equal to pressure at 2, and volume that's displaced at 1 is equal to the volume displaced at 2. Alright, next example, we have a 5-gallon bucket. It's being filled up with a hose that has a diameter of 2 inches. It takes 1.5 minutes to fill a bucket up. What's the volumetric flow in gallons per minute and the velocity of the fluid through the hose in feet per second? So first of all, we have a Q equals a volume divided by time. So we can say it is 5 gallons divided by 1.5 minutes. It's going to give us a volumetric flow rate of 3.3 gallons per minute. And that's also wrote as 3.3 GPM. You'll see that quite often. So let's do a conversion here. 3.3 gallons per minute times 1 feet cubed divided by 7.48 gallons times 1 minute divided by 60 seconds. And we're going to get 0.00735 feet cubed per second. We're also going to need to know the area of our hose. So we'll look at that real quick. Area equals 1 inch squared times pi. Gives us 3.14159. The rest of it inches squared. So our volumetric flow rate is also equal to Q equals velocity times area. So our 3.3, actually we better use the 3.141 inches squared times 1 feet squared, 44 inches squared. It's going to give us 0.0218 feet squared. That way we have like units for our volumetric flow rate. So we take our 0.00735 feet cubed per second times this by our divide this by or 0.0218 feet squared. And we're going to get 0.337 feet per second. So 3.3 GPM, and the velocity inside the hose is 0.337 feet per second. Okay, that is it.